So chapter 10.2 is about the light-dependent reactions in photosynthesis. So we need to understand how the light from the sun is a form of energy and how it's transferred to make chemical energy in the form of an organic molecule or sugar. So it starts off by saying chloroplasts are solar-powered chemical factories. Which is true. They're just pumping out organic molecules and they're taking energy from the sun. And so this happens with the thylakoids. So light-dependent reactions are when we take energy from the sunlight and we transform it into ATP and NADPH. The Calvin cycle will later take the energy that we stored in ATP and NADPH, later take those to make organic molecules, but the light-dependent reactions store their energy in the form of ATP and NADPH. So this is a little bit about sunlight. Light is energy, and it travels in waves. And wavelength is the distance between the top of two waves. So like if there's two waves right here, the wavelength is the distance between the crest of those two waves. And wavelength determines the type of electromagnetic energy. So it could be radio waves, sunlight, ultraviolet rays, X-rays, whatever it might be. And so the wavelength determines what color the light is going to be in addition to what type of energy it's going to be. And so we talk about this thing called the electromagnetic spectrum, which is all kinds of waves that exist. Invisible light just consists of a very specific amount of wavelengths that produce colors that your eyes can see and turn into images in your brain. And photons are like little bits of light that act as distinct particles. We're going to talk about that in a minute. So here is the electromagnetic spectrum. It consists of everything from gamma rays to radio waves. Invisible light is just a tiny, tiny little bit of this. And visible light extends from wavelengths of 380 nanometers to 750 nanometers. So we have these things called pigments. Pigments are in your skin, they're in your clothes, they're in everything. But chloroplasts have green pigment in them that absorb the light energy at different wavelengths. So if the wavelengths are not absorbed, they're either going to be transmitted, which means they go right through, or they're going to be reflected. And so the reason that leaves look green is because they reflect green light at you. So the wavelength of light that bounces back at you into your eyes and you see green is the green wavelengths. So light coming from the sun has all colors in it, all wavelengths. The ones that get transmitted and reflected are the green ones because they don't get absorbed by the chloroplast. But everything else does get absorbed by the chloroplast. And so there's this machine called a spectrophotometer, which can tell you about a pigment's ability to absorb that wavelength. And basically what happens is the machine, it looks like this, it sends a wavelength of light, you determine what it is, through a sample. And it will measure how much of that light comes through on the other side. So if we have a solution of chlorophyll, which remember does not absorb green light, and we send the wavelength of green light right through the chlorophyll solution, none of it's going to be absorbed. So at the end, the spectrophotometer, the machine that reads it, is going to see, okay, all of the light came through. We know how much we sent through, and we're getting back 100% of it. That is very different than if we sent through, so chlorophyll absorbs blue light. So if we send blue light through, it's all going to get absorbed. None of it's going to come out on the other side. So we're going to see a very low transmittance or high absorption. So that means that it was all absorbed. That's how a spectrophotometer. And so we can have something called an absorption spectrum, which is a graph that shows which wavelengths get absorbed by a specific pigment. And so the absorption spectrum of chlorophyll A, which is one of the pigments in a chloroplast, suggests that violet, blue, and red light work best for photosynthesis. So here is our absorption spectrum for the different kinds of pigments that are in photosynthesis. So here are the different wavelengths of light, and this is how much light gets absorbed by each of them. So if you look at chlorophyll A, it absorbs a lot down here in this region, in the blue-violet region, and a lot up here in the red region. But in the green region, it absorbs almost nothing because it's reflecting that light and not absorbing it. Then there's also something called chlorophyll B, which absorbs a little bit more of the blue light and a little bit of red light, but again, no green light. Then there's another pigment called the carotenoids, which absorb less purple light, more blue light, a little green light, and that's it. So this is the absorption spectrum. It shows how much that pigment absorbs at the different wavelengths. And that is different than an action spectrum, which shows so absorption spectrums show how much light is absorbed. Action spectrums show how effective a process is at that wavelength. So for example, this is photosynthesis. It shows you how effective it is at different wavelengths. So it's very effective in the blue-violet region, and it's very effective in the red region. But in the green region, it's very not effective. So this is a combination of all those three pigments working together. So absorption spectrum shows you the amount of light absorbed by a pigment at a specific wavelength. Action spectrum is for a process and shows you how effective that process is at the different wavelengths. We're going to skip this. So chlorophyll A is the main photosynthetic pigment. It's the main one in the chloroplasts. It does the most of the absorbing and most harnessing of light energy. But then we also have, like I said, chlorophyll B is called an accessory pigment because it's not the main one. And it's used to broaden the spectrum so that we can absorb multiple wavelengths of light. And then we have another thing called carotenoids that absorb excess light that might cause damage to the chlorophyll. So they get more spectrum of light that the chlorophyll can't handle. Okay, so here's how pigments work. When they absorb a photon of light, a piece of light, it goes from a ground state to an excited state. So it absorbs the energy and gets excited. And this is very, very unstable. Okay? And so what happens is the excited electrons are going to want to fall back down. And it gives off energy called fluorescence. You don't need to know about this. Okay, so basically a photon of light will hit the chlorophyll and the electrons get excited. If this energy is not harnessed to do anything else, then you'll see it light up. But we're going to harness it to use something else. So in the light-dependent reactions, we have these things called photosystems. Photosystems consist of